Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the optical communication. Today in this video, we are going to talk in detail about the fiber to fiber joint losses. So we are going to see what are the fiber to fiber joints, what is the requirement of having the fiber to fiber joints. Then we are going to see the different losses that are happening if I have multi-mode fiber joints and when we have the single mode fiber joints. So for both of the cases, step index fiber as well as graded index fiber, we are going to see how the losses will be arising and mathematically we will compute them. So this video is going to be really interesting one and informative one, and I hope all of you are watching this video with your utmost attention. So let's start the discussion for the today. So what is fiber to fiber joint? So when I want to do the communication over long range, let's suppose I want to send the signal to a distance which is 4000 km away. So at that time I cannot use single optical fiber. We have already seen the construction of the optical fiber, and there we have seen the limitation of the construction that we cannot generate a very long optical fiber. So here we have to connect some of the optical fiber so that signal can travel to a longer distance. Right, so here we are using multiple optical fibers which are connected with the help of joints, and in these joints how the light is traveling from the one optical fiber to another, what are the losses that are happening, why we have the losses which are arising, and what are the various parameters upon which it depends, and what are the mathematical parameters of these losses. These things we are going to see in this video. So basically if I classify the joints, we will be having the different kind of joints like the splices, the connectors and the couplers. So in the three upcoming videos we are going to talk in detail about all three of them. First we are going to talk about the splices, then connectors, and last couplers. So what are the splices? Splices are semi-permanent or the permanent joints. So if I have some permanent joint or semi-permanent joint between the two optical fibers, so these are not easily destroyed, right? So these are almost semi-permanent or permanent joints which will be staying there for a long time, and we are not able to remove these joints very easily. So these joints are called the fiber splices. After that, coming to the fiber connectors. Fiber connectors are removable joints, which means I can easily remove them. So these are allowing me easy, fast and manual coupling and uncoupling of the fiber. So whenever I want I can do the coupling, and whenever I want I can remove the coupling. Whenever I want I can make the joint, and whenever I want I can remove the joint. So this is how the fiber splices are different from the fiber connector. Fiber connector are not permanent, whereas fiber splices are the permanent joint. Coming to the fiber coupler. So fiber coupler, as the name suggests, is going to couple a power from the one optical fiber to another optical fiber. So it is going to couple a proportion of light from main fiber into the branch fiber, right? So we will be having some transmitting fiber and we will be having some receiving fiber. Both of them are connected. So when the power of light is coupled from this fiber to this fiber, it is coupled with the help of the couplers. So we have fiber splices, fiber connectors and the fiber couplers. All of them are the bidirectional devices, right? So light can travel from any direction to any direction. If I have splices, connectors or couplers, we can couple the light from one fiber to another, from transmitting to receiving fiber as well as receiving to transmitting fiber as well. So both directions of propagation of light is possible with the help of these fibers. So we can do the two-way communication with the help of these connections, right? So now coming to the fiber alignment and joint losses. So what are the different losses? How we can categorize the different losses? So the losses which are occurring at the interface. So if I am connecting two fibers, so this is the first fiber, this is the second fiber, at the interface we will be having some losses. So the optical losses at the interface will be there even if I have the properly connected fibers. So even if I have very smooth ends, and even if I have the perpendicular to the fiber axis which are perfectly aligned. So if their perpendicular axis is perfectly aligned, if they are smooth and if they don't have any misalignment errors, then also they will be having some losses which are present due to the Fresnel's reflection. So now Fresnel reflection, what does it word mean? So reflection of the light which is transmitting from the transmitting fiber to the receiving fiber. So when this light reflect back into the transmitting fiber, so small portion of transmitting light reflect back in the transmitting fiber, and when the light comes back into the transmitting fiber, it has caused the attenuation of the light in the receiving fiber. So it has caused the attenuation. So now coming to the Fresnel's reflection coefficient, how we can measure what kind of attenuation would be there due to the Fresnel reflection. So due to the step changes of the refractive index at the interfaces, we will be having the Fresnel reflection. So now if I have perfectly same refractive index at the interface, Fresnel reflection would be least. So now this is the R which is giving me the fraction of the light that is reflected with the help of Fresnel reflection. So it is dependent upon the refractive index of the core and the refractive index of the medium that is separating the two fibers. So here let's suppose the medium is air. So refractive index of the medium is N, refractive index of the core is N1, right? So Fresnel reflection coefficient is given as N1 minus N upon N1 plus N square. So this is how I can find out the fraction of light that is reflected due to the Fresnel reflection. And now the loss. How I can measure the loss? With the help of minus 10 log 10 1 minus R. So I can use this R, I can take 1 minus R and I can take minus 10 log 10, and it is going to give me the loss in dB with the help of Fresnel reflection. With the help of Fresnel reflection, whatever losses are there, we can parameterize them with the help of fraction of light that is reflected, and then the losses as 1 minus R of 10 log 10. Right, this is how we can mathematically parameterize the Fresnel reflection. So now coming to the index matching fluid. So what is the index matching fluid? I told you, because here we have the changes in N1 and N. If I take both N1 and N to be equal to N1, if I take the medium which is having the refractive index which is equal to the refractive index of the core, so light will travel towards the core only. There will be no reflection or refraction due to the refractive index of the medium, right? So now here if I take N is equal to N1, so R will be 0. So losses due to the Fresnel reflection would be 0. Right? So theoretically it will become 0 when I take a medium which is having the refractive index equal to the refractive index of the core. So index matching fluid is the fluid which is having the refractive index equal to the refractive index of the core, and it is placed between the two fibers, and now at this condition I will be having the 0 Fresnel losses. So now coming to the connection problems. What are the different problems apart from the Fresnel reflection? What are the different problems that we have due to which we will be having some losses that are incurred during the joints that we are making? So these are the connection problem. First, we have the different core and cladding radius. We are going to parameterize it as well, that due to the different core and cladding radius, how we will be having some losses that are generated. Mathematically, we are going to see that. Different numerical aperture of relative refractive index differences. So now if I have the different numerical aperture and different relative refractive index differences, then also we will be having the losses present at the joints. So the two fibers, if they have different numerical aperture, the two fiber, if they have the different relative reflective index differences, two fibers that have different core cladding radius, then also we will be having some losses at the joints. So if I have different refractive index profiles alpha, so if the different refractive index profile would be there for the two fibers, again the losses would be there. So fiber faults, like if I have the core ellipticity, core would be present in the elliptical shape, or we will be having the core concentricity. So these problems are arising due to the fiber faults, and the fiber faults are again going to cause some problems when we have made the joints. So now all of these losses are the intrinsic joint losses. So these losses are present within the fiber only. Apart from the losses which are present intrinsic to the fiber, we are going to talk about the total intrinsic loss inside the fiber as well, mathematically how we can do that. So after that we will be having some fiber misalignment losses. Means if I have two fibers, how I am aligning them in the space, this is also going to tell me how much losses we have incurred. So we will be having three types of alignment of the fibers. First is the longitudinal misalignment. The longitudinal misalignment means in the longitudinal direction. So So now here, let's suppose these are my two fibers. So these are two fibers which are connected. So now when I connect them, I am not able to connect them properly, so that if the proper connection would be like this, they should be connected end to end, but they are not connected end to end in the longitudinal direction. So either the difference between them is very less or the difference between them is very large. So at these two cases we will be having the longitudinal misalignment. Second is the case when we have the lateral misalignment, when the two fibers are laterally misaligned. So now here the two fibers are aligned in the longitudinal direction, but they are misaligned. You can see here we have the misalignment in the lateral direction. So one fiber is like this and one fiber is like this. So now here the area which is covered for both of these fibers is going to tell me how much light is going to couple. So if I have very small area which is covered for both of the fibers, so the covering area which is common for both of the fiber is going to tell me how much light is going to align in these two fibers. After that we have the angular misalignment. Angular misalignment means the fibers are like this. So they have not come on the same angles. They should be 180-degree angle, but now they have some angle in between them. So this is how we will be having the different misalignments. So now which of them is very severe misalignment? If I have longitudinal misalignments, a lot of light can be propagated from the transmitting optical fiber to the receiving optical fiber, right? The losses would be very less, but the losses will become 10 times if I have the lateral misalignment. So let's suppose if I have 0.1 dB loss in the longitudinal misalignment, then I will be having the 1 dB loss for the lateral misalignment. So this is how the lateral misalignment becomes really severe than the longitudinal misalignment. So lateral misalignment is having greater losses per unit displacement than the longitudinal misalignment, because in the lateral the output light that is received by the receiver optical fiber depends upon the covering area which is common for both of the fibers. If this covering area is less, then the light which is transmitted from this fiber will not be able to couple to this fiber, and this is the reason the lateral misalignment is very severe and is going to give me a lot of losses than the longitudinal misalignment. So now coming to the multimode fiber joints. What are the multimode fiber joints? As I know, in the multimode fiber I will be having the different modes which are traveling inside the fibers, right? So if I consider the single mode, I will be having only one mode which is propagating through the fiber. So I have here in the multimode fibers the multiple modes which are traveling inside the fiber, and they are taking the light energy from one point to another point inside the fiber. So we will be having two types of fiber. First is the full numerical aperture fiber, and second is the equilibrium numerical aperture fiber. So what is the full numerical aperture fiber? In the full numerical aperture fiber, we consider all of the modes are having equal excitation, equal power or equal energy is transmitted with the help of all of the modes, right? But in the equilibrium numerical aperture fiber, I consider most energy is concentrated in the lower order modes only. So now when I consider that the most of the energy is concentrated in the lower order mode, I just need to couple the lower order mode from the transmitting to the receiving optical fiber, right? But this situation becomes too optimistic for us to understand, because in most of the practical consideration it does not happen that most of the energy is concentrated in the lower order modes. So let's suppose if I have two optical fiber, right? So here this is my first optical fiber, this is my second optical fiber, right? So here this fiber can allow 400 modes that can be passing through it, and this allow 500 modes that are passing through it. And when the light is traveling from 500 to 400 mode optical fiber, so 100 modes are lost. It is not going to accommodate these extra 100 modes that were present here. So the light energy which was there in this extra 100 modes is not going to come here, and here we are going to get some significant losses, right? But if I consider that the light energy is there only in the central modes, so let's suppose in the central 50 modes only I was having most of the energy, so it is able, because here we can accommodate 400 modes, it is going to accommodate the central 50 modes. So lower order 50 modes it is going to accommodate. So it is going to take most of the light from the transmitting optical fiber to the receiving optical fiber. But this situation becomes too optimistic. I cannot consider always and always all of the energy is concentrated in the lower order modes, and reverse is also not true. I cannot consider that the energy is equally distributed in all of the modes. So this becomes too optimistic and this condition becomes too pessimistic. But we are doing all of the calculations being too pessimistic, because we are going to get the worst possible outcomes, and then from the worst possible outcomes we will be seeing this is the worst condition in which my optical fiber will be able to behave, and then if it is able to behave or work properly in the worst possible condition, then it will be able to work very efficiently in the better conditions. So we are going to be too pessimistic, and then I will be computing and I will be having all of the computations, and then I will be using it on the practical conditions. So now the efficiency due to lateral misalignment. So the efficiency due to the lateral misalignment is going to be nearly equal to 16 n1 upon n square upon 1 plus n1 upon n raised to power 4 multiplied with 1 upon pi 2 cos inverse y upon 2a minus y upon a multiplied with under root 1 minus y square upon y upon 2a whole square. So now this is how I can get the lateral efficiency. So when I have lateral misalignment, I will be getting the efficiency with this method, where y is the lateral offset of the fiber core axis, how much laterally these two fibers are offset, and a is going to give me the core radius. Now n1 is the refractive index of the core and n is the refractive index of the medium, right? All of the things are otherwise constant. 2 is a constant, pi is a constant, right? So this is how you can find out the efficiency. And from the efficiency, if you want to calculate the losses, so the losses in the lateral direction is going to be equal to minus 10 log 10 eta lateral in dB. So this is how we are going to get the losses in the lateral direction for the step index fiber. And now if I have the graded index fiber, the graded index fiber LT is going to be equal to 2 upon pi y upon a alpha plus 2 upon alpha plus 1. So this is how we will be having the losses in the graded index fiber as well. So now here I consider y, the lateral displacement coefficient is in between the 0 and 0.2a only, right? So a is the core radius and alpha is the profile parameter, we all know. So eta lateral will be equal to 1 minus LT. Right, so here I will be having the relation between eta lateral and LT as well. So if I consider alpha is equal to 2, so here if you put alpha is equal to 2, here you will be getting 4 upon 3. So now here I will be getting 8 upon 3 pi into y upon a. So 8 upon 3 pi will be equal to 0.85. So LT will be equal to 0.85 y upon a for the graded index fiber, right, when we have the parabolic profile parameter or alpha is equal to 2. Now for the angular misalignment, the efficiency is going to be nearly equal to 16 n1 upon n square upon 1 plus n1 upon n raised to power 4 1 minus n theta upon pi n1 to delta power 1 by 2. So now what is delta? Delta is the relative refractive index, theta is the angular displacement in the radian, right? n1 is the refractive index of the core, n is the refractive index of the medium. So loss in the angular misalignment will be equal to minus 10 log 10 of eta angular or efficiency in the angular in dB. So here I have understood that how in the angular displacement for this case and for lateral displacement for this case we are going to have the losses. For the longitudinal misalignment we are not considering the losses because these losses will be very less as compared to the lateral misalignment losses and angular misalignment losses. So if I want to compute the overall losses, so we are going to compute the lateral or the angular misalignment losses. So these were the extrinsic losses due to the misalignment of the fiber. So now coming to the intrinsic losses. So first losses would be due to the misalignment of the core diameter, so which is called the LCD, right? So core diameter is CD, so misalignment of the core diameter is going to give me the losses as well, which is represented as LCD. So it will be equal to minus 10 log of 10 A2 upon A1 square, where A2 is the core radius of the second fiber, right? A2 is the core radius of 2 and A1 is the core radius of 1. So if the core radius of the second fiber, right, the receiving fiber is less than the core radius of the transmitting fiber, then the losses will be happening, which is equal to minus 10 log 10 A2 upon A1 square. But if the core radius of the second receiving fiber is greater than or equal to the core radius of the first fiber, which was the transmitting fiber, then the zero losses would be there, right? So I want the receiving fiber which is having the bigger core radius than the transmitting fiber. So now next come to the losses due to the numerical aperture differences. So we have seen how the losses is arising due to the core and cladding radius differences. Now coming to the second parameter, the numerical aperture differences. So here the loss in the numerical aperture is given when the numerical aperture of the optical fiber 2 is less than the numerical aperture of the optical fiber 1. When the numerical aperture of the second receiving optical fiber is greater, we will not be having losses. So numerical aperture when less than the numerical aperture 1. So numerical aperture of receiving fiber is less than numerical aperture of the transmitting fiber. Then the losses will be minus 10 log 10 Na2 upon Na1 square. Right, so this is how we will be having the losses due to the change in the numerical aperture as well. So now the loss due to different profile parameter. So I told you there would be losses due to different refractive index profiles as well. So if I have different alphas, different profile parameters, because of them also we will be having some losses. So this is called as loss due to R1. So it will be equal to minus 10 log 10 alpha 2 alpha 1 plus 2 upon alpha 1 alpha 2 plus 2 when alpha 2 is less than alpha 1. The profile parameter of second fiber is lesser than the profile parameter of first fiber. So if I take the profile parameter of first fiber to be 2, second fiber must have profile parameter 2 or greater than 2. So 2 or 3 I will be taking the profile parameter of the second fiber, or in between 2 or 3 as well, any number. So now here it would be 0 if alpha 2 is greater than equal to alpha 1. So if I compute all of the losses, if I add all of them, I will be having 10 log 10 A2 by A1 square minus 10 log 10 Na2 by Na1 square minus 10 log 10 alpha 2 by alpha 1 plus 2 upon alpha 2 plus 2. Now this, if I add all of them, so these are the log terms. When I add of all of the log terms, I will be getting the multiplication. So minus 10 log 10 is common. I will be having alpha 2 upon alpha 1. So this is A2 upon A1, A2 upon A1, Na2 upon Na1 whole square. So A2 Na2 whole square, A1 Na1 whole square. So A2 Na2 whole square upon A1 Na1 whole square multiplied with alpha 1 plus 2, alpha 2, alpha 2 plus 2, alpha 1. So all of the conditions are here. If A2 is greater than A1, if Na2 is greater than Na1, if alpha 2 is greater than alpha 1. Otherwise we will be having the zero intrinsic losses. So these are the 3 intrinsic losses and we have computed all of them, right? These were 2 extrinsic losses. So I hope you understood what are the intrinsic losses, what are the extrinsic losses. So now coming to the single mode fiber. In the single mode fiber, I know I will be having only one mode. So we will be having the lateral offset as well as the angular misalignment, right? So due to the modes, I will not be having any losses. So the lateral offset is given by T1, which is equal to 2.17 y upon w square in dB. So y is the offset factor in the lateral direction. So how much offset is there in the lateral direction? Y is going to give me, W is the spot size, and W will be equal to A 0.65 plus 1.62 V raised to power minus 3 by 2 plus 2.88 V raised to power minus 6 upon under root 2. So now we will be having spot size, which is calculated in the terms of core radius and the normalized frequency V. So now here if I change the W, then I will be having the different lateral offset, right? So lateral offset depends upon the spot size. Obviously, if I have larger spot size, the lateral offset is going to create big problem. If I have smaller spot size, so if the spot size is very smaller, if I have small misalignment, so in that scenario, if only the cladding is misaligned, if the core is aligned, so that scenario I will not be having any losses, right? But if these two are perfectly misaligned, in the small misalignment, it is possible that these two are exactly near to each other, but sometimes because of some lateral displacement, or we will be having the exact misalignment, so the zero power will be traveling from this fiber to this fiber, right? So if I have larger spot size, I will be having advantages as well as disadvantages. So if these are small shifted, we will be having small power which is leaked, right? Or small power loss will be there. Now coming to the angular misalignment. Angular misalignment is also computed in the terms of spot size. So it is represented as TA, which will be equal to 2.17 theta W N1 V A NA. So now here what is theta? Angular misalignment in radians. So if I take the angular misalignment, how much angle is there for the misalignment? This would be my theta, right? So theta would be angular misalignment, W is my spot size, and 1 is the refractive index of the core, V is the normalized frequency, A is the core radius, and NA is the numerical aperture. So this is how we can calculate the losses in dB for the single mode fibers as well. So I hope you understood all of the things that I have discussed in this video. If you have any doubt regarding any of the topic, you can put the doubt in the comment now, and I will be trying to resolve your doubt as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel, share it with your friends, and also give me your feedback. Thank you so much.